Hi all. This is going to be our first video for Math 120 Online, section 2.5, which we actually did some of back before spring break, but I'm going to kind of just go back to the beginning of it and recap it. So, I'm here in my basement. Lots of Legos back there behind me. Otherwise, it's just the basement. All right, so you can see this is the section 2.5 handout, which if you don't have, you can get off a Blackboard to follow along or to fill in or whatever. We're just going to go through it, and before the group exercises, I'm going to pause, or other parts too. I'll tell you to pause the video, and you could try and do some stuff on your own first, and then I'll go over it. That's kind of how it's gonna go. So I started filling in some things here already, and we already went over this in class too. So we're talking about vectors, and quantities in this world can be put into two groups, ones that involve direction and ones that don't, basically. And a vector quantity is something that involves a direction, like force and velocity and acceleration and momentum, all of these guys here. Whereas some other things, mass, temperature, energy, those are things you don't talk about what direction the temperature is pointing or things like that. Vector quantities are modeled with vectors, line segment with an arrow on the end, kind of like I drew right there. We'll draw lots of them. The notation that's typically used in a textbook for vector quantities is to put them in boldface, but we can't write boldface. So what we do is put this little vector hat on them right there. So you name of your vector, capital letter, sometimes lowercase, and basically you're putting an arrow on top of it, but we just put a little half arrow kind of because it just gets tedious to put a whole arrowhead on those things. And if you put these little things that look like an absolute value around a vector, by that we are only talking about the magnitude, how long that vector is, how big the force is, how fast the velocity is, and ignoring the direction. Hopefully this makes sense. Two vectors are equal if they point in the same direction and if they have the same magnitude. All right. Now, vectors are sort of new mathematical beasts, and we can do some operations with them, and one of the things we can do is add them together. So, for a couple examples here. So what if you had a vector pointing straight to the right, due east, magnitude 3, and then another one pointing same direction, but magnitude 5. All right, this one should really be a little bit longer to show that it's bigger than the 3. And hopefully it makes a lot of sense that when you add those two together, the result points in that same direction and has a length of 8. It's like if what I mentioned in class was the walking on one of those moving walkways in the airport terminal. And if the walkway is going 3 miles an hour and you're walking 5 miles an hour on the walkway, overall you're moving 8 miles an hour relative to the airport that's sitting still. All right, number 2, so what if we were pointing due east, and then we had this guy of magnitude 5 pointing the opposite direction? I hope it makes sense that the result would just be a vector length 2 pointing to the west. The bigger vector kind of wins the battle there. And that's like you're walking backwards on that moving walkway at the airport, and ultimately you'd be going 2 miles an hour backwards on that thing instead. Now here's where things get more interesting, when things don't point in the same or opposite direction. So what if you get this deal? Well, the way we add vectors is typically to draw one of them and then tack the other one onto the end of that. And the sum of those two vectors is the vector that goes from the beginning of the first one to the end of the second one. So this, with the 3 and a 3 here, this sum would end up pointing exactly northeast. And then the question is, well, how long is that guy? And the answer is not 6. This forms a nice little triangle, and you can do trigonometry or whatever to figure out how long that is. This is actually one of our nice 45, 45, 90 triangles, and you get 3 times the square root of 2. So in general, adding vectors, and this is how forces, multiple forces applying to the same object add up. We ultimately use the diagonal of a parallelogram. So if we have two vectors here, here's v and w, and they're sort of coming out of the same spot. To add those two guys together, so what's the resulting force if these represented forces? Well, they're coming out of the same location. I'm just going to move one and tack it onto the end of the other. So here's w tacked onto the end of v. Or you could put v onto the end of w like this. And the result, the sum, is the diagonal that goes from beginning all the way to the end. So this is what v plus w would look like. That's what we talk about using a parallelogram. When you complete those sides, you get a nice parallelogram. All right, so, and here's just another example. If we were to copy w down here or copy v here, the result would look like this. So here's v plus w, like so. And notice that the sum can be shorter than the actual two things you're adding together. If they point in opposite-ish directions, things can sort of cancel out a bit, and the result can be smaller. All right, here's kind of situation where we use these, and situations where we'll see them a lot. So, boat is facing due east. So if it was just sitting on a pond and the water wasn't moving, it would go 12 miles an hour straight east. So if we drew a vector for that, it would look like this, length 12. All right, but we're not on still water. We're on water moving north at 5 miles an hour. And so we think of the water's speed vector, and we're going to add that to the boat's. So going due north would be pointing straight up in our picture. And so what's the actual speed of the boat? And you could answer the question, what's the actual direction too? Well, if you connect beginning to end here, and we got a nice right triangle like so, it's just a matter of finding the hypotenuse of this right triangle. Now you might recognize 5 and 12, and remember that if you do the Pythagorean Theorem, 13 is what you get right there for that answer. And then you could figure out the direction too by doing some trig and figuring out what the measure of this angle is, but this question's not asking for that. All right. Another operation we can do with vectors is take a vector and multiply it by just a plain old real number. Now, real numbers are called scalars in mathematics sometimes, because when you multiply a vector by a real number, it scales them, shrinks or stretches it. So if this was v, for example, 2 times v, the vector 2v would point in the exact same direction, but be 2 times as long. Other examples, 3/2 v would be same direction, 1.5 times as long. 1/2 times v would be half as long, but point in the same direction. -1 times v, which we actually just write as minus v, that would be same length, but opposite direction. And so like -3 times v would be 3 times as long and point in the opposite direction. Now sometimes we get the xy plane involved, and then when we look at a vector, we can think about the point that it stops at, but we also think about breaking up a vector into vertical and horizontal pieces. So we can actually associate a direction to it just by thinking about angles in the xy plane measured from the positive x-axis, like we always have. And then we get 2 vectors here. We get this guy, which is called Vy, and this guy down here, which is Vx. And those are the vertical and horizontal components of v. If you added v and Vy and Vx together, the result would be the v that we have right there. Now, drawing this stuff in, you can make very nice right triangles, and this is a parallelogram, so this side is also a copy of Vy right there. So if going from v and the direction it points, you can easily get the 2 components, how long those guys are. And it's trig that we've been dealing with all semester long. the length of the horizontal piece. Well, if you just use SOHCAHTOA, the result ends up being length of V times the cosine of that angle. And the vertical one has a length equal to hypotenuse times sine theta. All right. So, if you haven't yet, we did this in class still, take a sec and compute the components of these three vectors. So for each one, you're given the length of the vector and the direction that it points. And it's just a formulaic thing from up above. So pause the video, work those out, then unpause, and we'll go over them. So pause, pause, pause. Okay. Assuming you paused and did that, well, your Vx would be 10 times the cosine of 30 degrees. And if you punch that out, you get about 8.6. And Vy is 10 times the sine of 30 degrees, which is 5 units. So just to briefly give you answers here. For these guys, 12 times the cosine of 81 is about 1.9. 12 times the sine of 81 is 11.9. And here we would have 6 cosine 45 and 6 sine of 45. And actually, if you think about that, what that looks like, we get the same result for both of these because the sine and the cosine of 45 are the same thing, and they both end up being about 4.2. So these formulas just came from knowing the hypotenuse and knowing theta, and then using SOHCAHTOA to get those formulas. The other way, knowing Vx and Vy and getting the other things, is like, well, knowing the two legs of a right triangle and figuring out the hypotenuse and the angle involved. In particular, those formulas end up giving you, well, Pythagorean Theorem is just this. Oops. A lot of messy stuff there. Little hat. The length of Vx squared, the length of Vy squared, add them up, take a square root. And here, if you know the two legs and you're trying to get one of the angles from SOHCAHTOA, that means the tangent function is involved. And the tangent of theta would be length of Vy over length of Vx. And then you could use an inverse tangent button on your calculator to get the angle. All right. So, a few examples and then some group stuff. All right, so here's a ball. It's launched in a certain direction, but we're able to know how fast it's moving horizontally and how fast it's moving vertically. You could think of either of those quantities separately. And so the question is, okay, what direction is it actually going and how fast is it going? So horizontal velocity 12 miles an hour. If we start drawing a picture here, that's like horizontal, a vector of 12, vertical, a vector of length 35, and if you add those together, that means this vector right here. Nice right triangle. And to describe its direction, well, if we think of a launched ball, we would probably want this angle. What's this measurement from horizontal that it's launched at? So this is our vector v, which represents the ball's trajectory or initial trajectory. And we're going to find the length of v, and we're going to find theta. So just a little Pythagorean theorem, length of v. If you want to pause and do it yourself, that'd be a great idea. But here I go. Well, 12 squared plus 35 squared. Maybe you recognize that one. It's actually a Pythagorean triple, and you get 37 miles per hour. Tangent of our angle would be 35 over 12. So our angle, it's launched at an angle from horizontal, which is the inverse tangent of 35 over 12. And if you punch that out, you get about 71.1 degrees. Okay. So, writing some notes. Got a few more problems we're going to go through. The other concept that comes up here is, especially when you're talking about forces, is static equilibrium. All right, an object that's not moving can have forces that are being applied to it, but the forces all add up to zero. Put this in boldface because it's the zero vector. That's why it's not moving. When you sit on your chair, gravity is pushing down, your chair is pushing up, but you're not going anywhere. All right, so these are very typical structural problems, adding up forces, trying to make things cancel out, stuff like that. All right, so we have a 25 kilogram weight. So it is hanging and gravity pulls down with a force of 25, and we're just going to measure forces in kilograms. Think of them as weights, which isn't quite accurate. Kilograms is a measure of mass. And there are two wires attached to this weight, and we're told the angles they form from vertical, like so. And so putting those in, well, one makes an angle of 35, so kind of like 35 degrees right there. And I don't know why that popped up. And the other makes an angle of 55, kind of like this. And the point is, so this weight is not moving. So these two forces have to add up and cancel out the force of gravity. Oops. So put a head on that guy. So if I were to take this one and copy it, try to copy it over here, so that our 35-degree angle is right here now, we basically get a triangle, right? A vertical side and these two sides. So that looks ultimately like this. And the thing is, these two sides, when they add up, they should exactly counterbalance. They should give you a vector that points straight up with a length of 25. So in other words, here's the triangle we have. Like this, where this needs to be 25, we know this is 55, and this angle in here is 35 degrees. And so when we're being asked for tension in the wires, like how many kilograms of weight is being pulled through those wires, it means finding these two sides. I'm going to call it X and Y. How long are those sides? All right. So a little geometry, and then good old trig that we've done before. So we have one angle in the triangle here. We don't know two of the sides. So this is going to be a triangle situation where we got to figure out angles. Now, this points straight up, and so does this side. We know this is 55 degrees. If you were to extend this down, this guy right here is an alternate interior angle for the 55, so this guy is 55 as well, which means this whole angle would have to be 180 minus that, so 125 degrees. I'm going to give some labels here to the corners. Well, so then angle A in the triangle right here, well, the whole thing is 125. If we take away 35, we end up with exactly 90 degrees, which I didn't do on purpose, but that's what we get. So angle A is 125 minus 35, which is exactly 90 degrees. So we're actually looking at a right triangle. In fact, if we were to redraw it, we have this, 25, a right angle, 55 degrees right there. And here's X and here's Y. And since it turned out to be a right triangle, we can use SOHCAHTOA. Now, if that wasn't a right angle, we'd have to use law of sines instead. All right, but, well, sine of 55 would be opposite over hypotenuse, which is X over 25. Cosine of 55 would be adjacent, Y over hypotenuse 25. So X is just going to be 25 sine 55. Y is going to be 25 cosine 55. Punching those out, we get, got my two numbers here, 20.5, and that would be a unit of kilograms. 14.3, and that would be a unit of kilograms. All right. So obviously new conceptual stuff here with putting together forces and making them add up, and they have to cancel out other things. All right, there's a couple group exercises on the next page. They don't quite involve forces like that. But I'm going to say, if some of this is making some sense, pause and see if you can figure out what's going on, or see if you can do these two. Otherwise, I'll go over them in just a sec. My hint for number 2, which is different than what I had before. Okay, never mind. No hint for number 2. This is forces and things pulling in certain directions. All right, pause that video, give these a try, see how they go. But I'm basically going to start going over them right now. So pause if you're going to pause. All right, number 1 is not bad. We've got horizontal and vertical speeds like the previous problem. We're just going to find total velocity and launch angle. So horizontally, 41, vertical, tack on 12. So how long is this, and what's that angle? And it makes a nice 90-degree angle right there. This is our vector v. So magnitude, square root of 41 squared plus 12 squared. Not a Pythagorean triple, you got to round it, and you get 42.7. And that's meters per second, because that matches what's in the problem. And tangent of theta will be 12 over 41. So theta is inverse tangent of 12 over 41. And out comes 16.3 degrees. So launched 42.7 meters per second, making that 16.3 degree angle from horizontal. Okay. So we have a steel ball on a wire. Gravity is pulling straight down, while a magnet pulls straight to the right. If you imagine this, if there was no magnet, the ball would just hang straight down on a wire, and that'd be the story. All right, there'd be 20 pounds of tension in the wire. But we turn on this magnet and it pulls the ball to the right, which would make it angle at, or sort of not lean, swing to the side at some angle and stay there. All right. So direction and magnitude of the total force on the ball. So if you think of the ball, we have 20 pounds straight down, and we have 15 pounds straight to the right. The result would come from making the parallelogram or copying one over to the other. Doesn't matter if you copy the 20 over here or if you copy the 15 down underneath. Either way, you get a right triangle, and you know the two legs. And I think here, well, you could describe the direction any way you want. Magnitude will be the length of the hypotenuse. But direction, let's call that theta. And we'll figure out the direction by figuring out what that angle is. So we're kind of saying, well, if you turn the magnet off, it hangs straight down. If you turn it on, it angles off to the side by that much. So first off, so here's V, our vector describing the total force on the ball. Well, again, magnitude of V, this is a right triangle, so we don't have to get too complicated with the law of sines and cosines. We can just do SOHCAHTOA and Pythagorean Theorem. Square root 15 squared plus 20 squared. It's actually a nice Pythagorean triple. It gives you 25. So the total force on the ball is 25 pounds. Direction, well, theta here, the two 20s are parallel to each other, which means theta here is the same alternate interior angles with that angle right there. So if we just figure out that angle, we'll have figured out theta. So we think about that. Here, let's put an A there. Angle A, tangent, so tangent because we know the two legs, although we do know the hypotenuse right now, so you could use sine or cosine. But tangent is opposite over adjacent, which would be 15 over 20, which is actually 0.75. So angle A, which is going to be angle theta, is inverse tangent 0.75. And if you punch that out, and I don't have it in front of me, so I'm going to have to punch it out real quick on my calculator. Here's my phone. La 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 la. 0.75 inverse tangent is 36.9 degrees. So, total force on the ball, direction and magnitude, 25 pounds of total force in the direction 36.9 degrees from vertical. All right, we said angle A and theta end up being the same. All right, that is all the 2.5 notes. We'll do some more vectors in 7.5 and then as we revisit 7.2 as well. But that's the end of this video.